The night sky has always captivated human imagination, but hidden within its beauty are cosmic monsters that make our worst nightmares look small. Stars are not always gentle sources of light. They can be violent, unstable, and unimaginably destructive. Some spin faster than anything on Earth. Some unleash beams of radiation that could sterilize planets, and others wait silently to explode with the force of billions of nuclear bombs. These are the most terrifying stars in the universe, objects so extreme they challenge the very limits of physics and remind us just how fragile our place in the cosmos truly is. WR104, the Death Ray Star. This star is one of the most feared cosmic objects known to astronomers, not because it is the largest or the brightest, but because of what it may unleash when it reaches the end of its life. Sitting around 8,000 light-years away in the constellation Sagittarius, this star is a Wolf-Rayet type, which means it is a massive star that has already burned through most of its nuclear fuel and is now violently ejecting its outer layers into space. These kinds of stars are among the most unstable in the universe, constantly shedding their mass in fierce stellar winds that travel at thousands of kilometers per second. The very existence of this star suggests instability on a scale that's hard to comprehend. But what makes it truly terrifying is its potential to unleash a gamma-ray burst, a beam of energy so intense that, if pointed directly at Earth, it could alter life on our planet in an instant. Wolf-Rayet stars are rare. Only a few hundred are known in our galaxy, and all of them represent ticking time bombs in different stages of their evolution. This one, however, has caught astronomers' attention for a very specific reason. When stars like this collapse, they often do so in a spectacular explosion known as a hypernova, which is even more energetic than a typical supernova. During this process, the star's core collapses, and the resulting physics funnels an unimaginably powerful jet of radiation outward in two narrow beams. These jets are the gamma-ray bursts. The destructive reach of such a burst is so vast that even from thousands of light-years away, if Earth lies in its direct line of fire, the consequences could be devastating. The potential danger comes from the star's orientation. Unlike many other massive stars, where the beams may point in random directions across the galaxy, this particular star's rotational axis seems to be aligned suspiciously close to Earth's position. Gamma-ray bursts are not wide blasts. They are focused, directional beams, like a sniper shot across the cosmos. If one of these were to erupt from this star and head our way, the results would be catastrophic for our planet's atmosphere. The burst would flood Earth with high-energy photons, breaking apart molecules in the upper atmosphere, destroying the ozone layer, and exposing the surface to lethal ultraviolet radiation from the sun. Even though the event might only last seconds, the long-term consequences could include mass extinctions, similar to or worse than some of the great die-offs in Earth's history. To put its destructive power into perspective, a gamma-ray burst from this star could release in a few seconds as much energy as our Sun will emit in its entire 10 billion-year lifetime. That's not just frightening, it's almost incomprehensible. Such energy would not hit us like a visible blast. Instead, it would be silent, invisible, and sudden. Earth's atmosphere would absorb the radiation, but the cost would be catastrophic. Entire ecosystems could collapse, food chains could disintegrate, and life as we know it would struggle to adapt to the aftermath. Adding to the unease, gamma-ray bursts are thought to have happened many times in Earth's history, potentially linked to past mass extinction events. Some scientists even suggest that one such burst may have contributed to the Ordovician mass extinction about 450 million years ago, when a large percentage of marine life suddenly disappeared. If that theory holds true, then the fear surrounding this star is not just speculation. It is grounded in the possibility that our planet has already suffered the wrath of such an event before. Another factor that makes this star especially terrifying is its life cycle stage. Wolf-Rayet stars are already nearing the end of their lives, meaning their explosive fates are not in some distant, unimaginable future. They are approaching fast on a cosmic timescale. While fast in astronomy could mean anywhere from thousands to hundreds of thousands of years, the fact remains that this star is on borrowed time. The moment it collapses, the question will not just be whether it explodes into a hypernova, but whether its gamma-ray burst will line up with us. What makes this even more unsettling is that we wouldn't have any warning. Light travels at a fixed speed, and this star is thousands of light years away. That means if the explosion has already happened, the gamma rays could already be racing toward us through the void, their arrival inevitable. The only signal we would ever receive would be the burst itself, and by the time it hit, the damage would be done. There would be no possibility of defending against it, no technology we could create to shield Earth from its fury. The entire event would unfold in silence, invisible, until it began unraveling our atmosphere. Yet, despite all this dread, it's important to note that not all scientists agree on the exact danger this star poses. Some argue that the rotational axis may not be perfectly aligned with Earth after all, and that even a slight tilt would mean the gamma-ray burst misses us entirely. Others point out that the probability of such a precise alignment is low given the vast scale of the galaxy. Nevertheless, the fact remains that it is close enough and aligned enough to keep astronomers watchful and concerned. It is, at the very least, a reminder of how fragile our position in the universe is and how powerless we are against the grand forces of stellar evolution. PSR J1903+12 the fastest spinning pulsar. This star holds a record that bends the limits of physics and imagination. Known as the fastest spinning pulsar ever detected, this object rotates at an unbelievable 716 times per second. To put that into perspective, if you were standing on its surface, something impossible of course, you would be moving at nearly a quarter of the speed of light due to the sheer rotation. That is faster than any man-made machine, faster than jet engines, and even faster than a kitchen blender on its maximum setting. This star is not just an astronomical oddity, it is a cosmic centrifuge, and it challenges our understanding of how matter behaves under such extreme conditions. At its core, this star is a neutron star, the ultra-dense remnant of a supernova explosion. When a massive star collapses, its core gets compressed into a sphere only about 20 kilometers across, yet with more mass than our Sun. That means this star packs solar mass into an object roughly the size of a city, creating gravity so intense that a teaspoon of its material would weigh billions of tons on Earth. What makes this particular star extraordinary, however, is not just its density, but the rate at which it spins. Astronomers call these objects millisecond pulsars because their rotation is measured in fractions of milliseconds. This one is the king of them all, spinning so fast that its surface is moving at over 150,000 kilometers per second. The speed of this star pushes the boundaries of what physics allows. Theoretically, if a neutron star spins too quickly, the centrifugal force at its equator could tear it apart, flinging matter into space. The fact that this star can hold together at such speeds suggests it is right on the edge of stability. Astronomers believe its rapid rotation may have been spun up by a companion star. Over time, material from a neighboring star was siphoned off and fell onto this pulsar, transferring angular momentum and making it rotate faster and faster. This process is called recycling, and it is the reason this star is rotating at such breakneck speed today. The physics surrounding this star is staggering. Its magnetic field, though weaker than some magnetars, still funnels beams of radiation outward. As the star rotates, these beams sweep across space like cosmic lighthouses, creating the pulsar effect we can detect here on Earth. Each pulse we see corresponds to a rotation, and in this case, the pulses are so rapid they appear almost continuous. Detecting and measuring such faint, rapid signals requires extraordinary precision. But doing so has given scientists a chance to probe the limits of neutron-star physics. To grasp the scale of its rotation, consider that the equator of this star is moving so quickly that it completes a full spin in just over 1 millisecond. If Earth rotated that fast, a single day would last less than a blink of an eye. The forces holding this star together are a delicate balance between gravity's crushing inward pull and the outward fling of centrifugal force. If it spun just a little faster, that balance could break, and the star might shed mass or even disintegrate. The fact that it hasn't done so yet makes it one of the most extreme natural laboratories for testing the laws of matter under conditions impossible to replicate on Earth. But there's also something terrifying about this star. While it is not aimed at Earth like a gamma-ray burst threat, its existence reminds us of how violent and unpredictable stellar evolution can be. A normal star, once shining peacefully, has already exploded, collapsed, and now spins faster than anything we could have imagined. The energy locked in such rotation is immense, and while it may not be an immediate danger to us, it is a stark illustration of just how chaotic the universe can be. Another eerie aspect of this star is its location. It resides in a dense globular cluster, an ancient swarm of stars packed tightly together. This makes stellar interactions more common, increasing the likelihood of close encounters, collisions, or mass transfers between stars. In such an environment, neutron stars like this one can be pushed to extremes, gaining speed, magnetic anomalies, or even swallowing companions. In this crowded cosmic neighborhood, stars live violent lives. This star also forces astrophysicists to reconsider the limits of neutron star matter. Neutron stars are composed of degenerate matter, where atomic nuclei have been crushed into neutrons under immense gravity. The rapid rotation of this star may be distorting its shape, flattening it into an oblate spheroid rather than a perfect sphere. The physics inside such a body is still largely theoretical, but studying its spin offers clues about what happens when matter is squeezed beyond nuclear densities. For instance, some models suggest that inside such a fast-spinning star, exotic forms of matter could exist, like strange quark matter or hyperons, particles that don't normally exist in ordinary conditions. For all its scientific intrigue, this star's terrifying aspect lies in its reminder of how fragile our assumptions are. We like to think the universe follows rules we understand, but then a star like this comes along and pushes those rules to their breaking point. If neutron stars can spin this fast without flying apart, what else might they be capable of? Could there be pulsars even faster, perhaps spinning hundreds of times more per second, hidden in the universe waiting to be discovered? If so, then this star is not just an outlier, it's a clue that the cosmos has far more extreme monsters still lurking out there. SGR 1806-20, the magnetar monster. Among the most terrifying stars ever observed, this one stands as a reminder that some stellar objects don't need to explode or collapse into black holes to wield unimaginable destructive power. This star is a magnetar, a rare type of neutron star with magnetic fields trillions of times stronger than Earth's and even thousands of times more powerful than those of normal pulsars. located about 50,000 light-years away in the constellation Sagittarius, it may seem distant enough to be harmless. Yet in 2004, it unleashed a flare so violent that its effects were felt here on Earth. In a fraction of a second, this star released more energy than our Sun emits in 150,000 years. The blast was so intense that it briefly altered Earth's ionosphere, a region of the upper atmosphere critical for radio communication. That means an event happening halfway across the galaxy still left a measurable scar on our planet's atmospheric systems, a terrifying demonstration of raw cosmic power. What makes this star truly monstrous is the mechanism driving such ferocity. Magnetars are neutron stars, themselves already one of the densest objects in existence. But what sets them apart is their magnetic fields. Imagine a star the size of a city with a magnetic field so extreme that it could strip information off a credit card from a distance of half the Moon's orbit. This star's magnetic field is roughly a quadrillion times stronger than Earth's. When such an immense field becomes unstable, it can suddenly rearrange itself, cracking the star's crust in what is called a starquake. These quakes are catastrophic, releasing bursts of gamma rays and X-rays that rip through space with devastating energy. In December 2004, one of these starquakes occurred, producing the brightest cosmic explosion ever recorded coming from outside our solar system. To appreciate how terrifying this event was, consider the scale. The flare lasted only a tenth of a second, but released more energy than the Sun has radiated in its entire history up to now. And yet this star is 50,000 light-years away. If it were closer, say within 10,000 light-years, the radiation could have seriously damaged Earth's ozone layer, leading to massive disruptions in climate and biosphere stability. The fact that our planet was so far away is the only reason life on Earth continued uninterrupted. It was a cosmic warning shot, a reminder that even stars across the galaxy can shake our environment in ways we barely understand. The December 2004 event was recorded across the world, with satellites and detectors lighting up almost instantaneously. The blast was so powerful it briefly blinded instruments designed to study gamma rays, overwhelming their sensors. Earth's magnetic field reverberated with the shock, and the ionosphere swelled with the influx of energy. Astronomers later calculated that the burst was so luminous that if our eyes could see gamma rays, the star would have outshone the full moon despite being tens of thousands of light-years away. The sheer enormity of this flare forces us to confront just how fragile our atmosphere really is against external forces. But this star's terror does not come from one flare alone. Magnetars like it are known for producing repeated outbursts. While the 2004 event was the most extreme, smaller but still dangerous flares erupt from time to time. The physics of how these magnetic monsters evolve is still poorly understood, but scientists believe they form when massive stars collapse and their cores are left spinning rapidly. The faster the spin, the more intense the magnetic dynamo inside, and the result can be a magnetar rather than a standard neutron star or pulsar. The catch is that these objects don't stay magnetars forever. Over tens of thousands of years, their magnetic fields decay, making them relatively short-lived by cosmic standards. But during their brief lives, they are among the most violent stellar objects in existence. This star is also a sobering reminder of cosmic vulnerability. If such a magnetar were to exist within a few thousand light-years of Earth, humanity might not survive its fury. A direct giant flare aimed at Earth could strip the ozone, irradiate the surface, and cause a biological catastrophe. Magnetars are like hidden cosmic landmines, scattered randomly throughout the galaxy, invisible until they explode. We only know of a couple dozen confirmed magnetars, but astronomers suspect many more lurk unseen, waiting for their next eruption. Adding to its mystery, This star is surrounded by a nebula of gas and dust, evidence of its violent birth in a supernova. The nebula itself glows faintly in X-rays, illuminated by the magnetar's persistent emissions. Every observation of this star deepens our understanding of high-energy astrophysics, but also amplifies our unease. For here is a star that doesn't need to go supernova, doesn't need to collapse into a black hole, and doesn't need to be nearby to demonstrate its lethal capabilities. It can reach across the galaxy and still leave a fingerprint on our planet. In the grand scale of cosmic threats, this star embodies the unpredictability of the universe. It shows that even when we think we are safely removed from celestial violence, we are not immune. Its 2004 flare was a historic moment for astronomy, but also a chilling reminder of how small and exposed Earth is in the galactic neighborhood. And while scientists study it for insight into exotic physics, for the rest of us, it represents something far more primal, a sleeping giant that, with one twitch, can shake the very shield protecting life on Earth. Vela Pulsar, the Lighthouse of Doom. The Vela Pulsar is one of the most iconic and terrifying neutron stars in our cosmic backyard, and it has earned its reputation as the Lighthouse of Doom. Born from the violent death of a massive star, this pulsar is the remnant of a supernova explosion that occurred roughly 11,000 years ago. Located about 1,000 light-years away in the constellation Vela, it is relatively close in astronomical terms. Close enough that its radiation pulses are among the brightest and most studied. What makes the Vela Pulsar so terrifying is the way it emits beams of deadly radiation, sweeping through space like a cosmic strobe light. Every time it spins, its magnetic poles unleash concentrated streams of energy, including X-rays and gamma rays, that cut across the void like interstellar searchlights. Any planet unlucky enough to be in the path of those beams would be bathed in radiation strong enough to sterilize its surface instantly. At its heart, the Vela Pulsar is a neutron star only about 20 kilometers across, yet it contains more mass than the Sun. Its density is so extreme that a single teaspoon of its matter would weigh billions of tons on Earth. What makes this star uniquely disturbing is its rotation speed and energy. The Vela Pulsar spins about 11 times per second, which may not seem fast compared to some millisecond pulsars, but considering the mass it holds, it is an astonishing display of angular momentum. Each spin powers the beams of radiation that fan out into space, and because they are so focused, they appear as rhythmic pulses when observed from Earth. That pulsing is how pulsars got their name. In the case of the Vela Pulsar, those pulses are so strong that they dominate certain regions of the gamma-ray sky. The pulsar's nickname, Lighthouse of Doom, is more than poetic. It is a stark reflection of the danger such an object poses. Imagine a lighthouse on Earth whose beam doesn't just light up the sea, but burns anything it touches. That is what the Vela Pulsar represents on a cosmic scale. Each time its beams sweep past, they carry with them radiation that would obliterate biological life on any nearby world. If Earth were positioned within the deadly sweep of its strobe, we would not survive the onslaught. Thankfully, we are not in its line of fire, but its proximity is still unsettling. Its pulses are bright enough that we detect them easily, proving just how powerful they are, even across hundreds of trillions of kilometers of empty space. Adding to its reputation, the Vela Pulsar is also known for a phenomenon called glitches. Unlike most pulsars that slow down steadily over time, the Vela Pulsar occasionally speeds up suddenly, as if something deep inside it has snapped. These glitches are thought to be caused by the superfluid interior of the neutron star, where frictionless neutron matter shifts and transfers momentum to the outer crust. When that happens, the pulsar's rotation jumps forward abruptly. These glitches are so dramatic they can be measured here on Earth, making the Vela Pulsar one of the most closely monitored neutron stars. From a human perspective, these glitches are terrifying. They are like sudden lurches of a cosmic engine that remind us the pulsar is unstable and still evolving in violent ways. The Vela Pulsar is also embedded in the Vela supernova remnant, a vast cloud of gas and dust left over from the explosion that created it. This remnant stretches across the sky and glows in multiple wavelengths, a reminder of the titanic force that birthed the pulsar. The supernova that created the Vela Pulsar would have been a blinding event to ancient humans, possibly outshining the moon for weeks. Today, the remnant is still expanding, and at its heart lies the pulsar, tirelessly sweeping its deadly beams across space. That haunting combination of a beautiful nebula surrounding a deadly core makes the Vela system one of the most fascinating and terrifying stellar remnants in our galaxy. From a scientific standpoint, the Vela Pulsar provides critical insights into neutron-star physics and the behavior of extreme matter. Its radiation pulses and glitches help astronomers probe the interior of neutron stars, testing theories that cannot be verified in laboratories on Earth. But from a broader perspective, it is a sobering reminder of cosmic violence. The pulsar is not an abstract object. It is a real, nearby star corpse, sending out lethal beams with mechanical precision, indifferent to whatever might lie in their path. The danger it represents is not immediate for Earth, but its very existence proves that the galaxy is filled with such threats. For every pulsar like Vela we can detect, there may be countless others whose beams do not point toward us, rendering them invisible. If just one of those were close enough and aligned with Earth, the result could be catastrophic. The Vela Pulsar, with its powerful radiation and sudden glitches, embodies the duality of awe and terror that defines the cosmos. It is a lighthouse, yes, but one whose light is a harbinger of destruction, not safety. RxJ 1856.5-3754- the Cannibal star. This star is one of the most unnerving stellar remnants known to science, not because of wild flares or devastating beams of radiation, but because of its sheer, incomprehensible density. It is a neutron star, an object created when a massive star exhausts its fuel, collapses under its own gravity, and leaves behind a core compressed so tightly that protons and electrons fuse into neutrons. The result is a city-sized object containing more mass than the Sun. The terrifying part is how this star embodies the limits of matter itself. If you could somehow scoop a teaspoon of material from its surface and bring it to Earth, that teaspoon would weigh billions of tons, enough to outweigh mountains. This star is a cosmic testament to the crushing force of gravity, showing us what happens when nature reduces matter to its most extreme form. Unlike some of the more flamboyant pulsars and magnetars, this star appears deceptively quiet. It does not emit dramatic pulses of radiation or unleash violent flares that can be easily observed. Instead, it glows faintly in X-rays, its surface temperature still scorching at around 700,000 degrees Celsius, despite being hundreds of thousands of years old. Its quiet nature is precisely what makes it eerie. It is not dead, but it is not alive in the way normal stars are either. It sits in the void, slowly cooling, a stellar corpse stripped of its former brilliance, now reduced to a naked ember of unimaginable density. This stillness, combined with its terrifying physical properties, has earned it the chilling moniker of the Cannibal star. What makes this neutron star especially terrifying is its gravitational pull. The surface gravity is around 100 billion times stronger than Earth's. That means if you stood on its surface, an impossible feat, you would be instantly crushed into a thin smear of subatomic particles. Light itself struggles to escape, bending around the star due to its intense curvature of space-time. In fact, One of the reasons this star is so fascinating to scientists is that it appears to be almost featureless when observed through telescopes. Unlike other neutron stars that exhibit hotspots or irregularities, this one shows an almost perfect thermal spectrum. Some astronomers suggest this could mean its surface is coated in a thin layer of condensed iron, or even in a form of exotic matter that smooths out its emissions. The lack of features makes it difficult to study, adding to its mystique and menace. The Cannibal star's nickname arises not from any radiation beams, but from the theoretical possibility that stars like it can consume anything that strays too close. With its intense gravity, it could rip apart asteroids, planets, or even smaller stars that wander into its grasp. Matter falling onto its surface would be accelerated to a significant fraction of the speed of light before smashing into its crust, releasing colossal amounts of energy in the process. In this way, neutron stars can act like cosmic predators, silently lurking until something drifts within reach. This star, sitting relatively close to us at about 400 light-years away, is among the nearest neutron stars known, making it all the more unsettling to study. Its proximity places it in a category of local monsters, not distant threats, but ones within our galactic neighborhood. There is another eerie layer to this star, the possibility that it is more than just a neutron star. Some astrophysicists have speculated that stars like this could contain exotic forms of matter, such as strange quark matter. If true, it would mean that the very laws of particle physics are being rewritten inside its core. Such matter might be more stable than neutron matter, raising the horrifying possibility that if such material ever escaped and interacted with normal matter, it could trigger a chain reaction, converting everything it touched into more strange matter. While this remains a theoretical scenario, it illustrates how little we truly understand these stellar corpses and how dangerous they could potentially be. This star also reveals something profound about the fate of massive stars. Our Sun, for example, will never become a neutron star. It is too small. But stars 8 times or more massive than the Sun can collapse into neutron stars after their supernova death throes. The Cannibal star represents what happens when a star larger than our Sun lives fast, dies violently, and leaves behind one of the most extreme objects in existence. It is a reminder that stars are not eternal, and when they end, they often leave behind remnants that are even more dangerous than their original forms. Though silent and dim, this star remains one of the most closely studied objects of its kind because of its potential to teach us about matter at nuclear densities. It is almost like a cosmic laboratory, one that no human technology could ever replicate on Earth. Yet it is also a silent executioner. It doesn't need to emit flares or beams to be terrifying. Its very nature is lethal. Anything unlucky enough to approach it will never return. The Cannibal star is a paradox of the night sky, visually unremarkable, yet physically one of the most extreme objects in the universe. It is a quiet killer, a relic of stellar violence that continues to exist as a monument to gravity's power. For astronomers, it is an object of fascination. For the rest of us, it is a stark reminder that beauty and danger often go hand in hand in the cosmos, and sometimes the deadliest threats are not the brightest explosions, but the silent predators that endure long after their fiery deaths. PSR B1257+12. The Pulsar with Dead Worlds. This pulsar is one of the most unsettling stars in the cosmos, not only because of its nature as a stellar corpse, but because it is surrounded by planets, worlds that exist in one of the most hostile environments imaginable. After the violent supernova explosion that created it, what remained was a neutron star spinning with precise regularity, blasting beams of radiation across space like a deadly lighthouse. Against all odds, astronomers discovered that this pulsar hosts at least 3 planets orbiting it. At first, the idea of planets surviving or forming around such a destructive remnant was astonishing. The very existence of planets around such a star is a mystery in itself. They may be remnants of a destroyed stellar system, fragments of worlds that were shattered and reassembled by gravity. Or they could be entirely new planets, formed from the debris left behind after the supernova. Either way, these worlds exist in a realm where no life as we know it could ever thrive. The radiation emitted by the pulsar would strip away atmospheres, scorch surfaces, and sterilize everything with a constant barrage of deadly particles. Unlike the warmth and light we associate with stars like our Sun, this star provides only destruction. Its planets are not havens, but tombs, silent, irradiated worlds circling endlessly around a killer. The planets themselves are fascinating in their bleakness. They are roughly Earth-sized, rocky in composition, and locked in tight orbits around their pulsar host. To the untrained eye, they might look like familiar terrestrial planets, perhaps even capable of supporting oceans or atmospheres under the right conditions. But appearances are deceiving. The intense radiation makes them uninhabitable in every sense. Any water would be boiled away, any molecules necessary for life shredded apart. These planets are, in essence, the corpses of worlds, lingering as eternal reminders of the devastation that their parent star unleashed. What makes this star even more chilling is how it warps our perception of planetary systems. We are used to thinking of planets as signs of potential habitability, worlds that might hold alien life, or at least echo the Earth's environment. But this system reveals the darker side of planetary formation. Not all planets exist in nurturing conditions. Some form in the aftermath of stellar destruction, doomed from the very start. These planets orbit their star not in hope, but in despair, locked in the gravitational grip of a stellar corpse that will never allow life to flourish. It is a planetary system of death, a cosmic mausoleum where worlds orbit in silence, scorched and lifeless. And yet, for astronomers, this star is invaluable. It was one of the very first pulsars discovered to host planets, proving that planet formation is not limited to young, healthy stars like our Sun. Planets can arise or survive, even in the harshest and most improbable environments. This revelation expanded our understanding of the universe, but it also introduced a terrifying possibility that not all planets are hopeful candidates for life. Some are forever cursed to orbit monsters, condemned to eternal radiation and silence. This star and its dead worlds embody one of the most haunting truths of the cosmos, that the universe creates not only beauty and possibility, but also desolation and doom. The planets orbiting here are not homes, not potential havens, but worlds that serve as reminders of the destructive power of stars. They are echoes of catastrophe, circling endlessly in a system where life has no chance to exist. HD 189733b's host star, Glass Rainmaker. This star is a terrifying example of how a stellar system can be as deadly as it is fascinating. Orbiting this star is the infamous exoplanet Glass Rainmaker, a world famous not for its size or location, but for the extreme and violent environment its host star creates. The star itself is a relatively ordinary main sequence star, similar in many ways to our Sun, yet its proximity to Glass Rainmaker transforms it into a force of unimaginable destruction. The planet orbits incredibly close to the star, much closer than Mercury orbits the Sun, exposing it to intense heat, extreme stellar winds, and high-energy radiation that would obliterate any atmosphere similar to Earth's. This setup turns the system into a hellish laboratory of extremes, where physics manifests in brutal and spectacular ways. Glass Rainmaker has become famous for the bizarre weather generated by the star's relentless bombardment. Temperatures soar to thousands of degrees Celsius, and fierce winds whip at speeds of over 7,000 kilometers per hour, fast enough to erase almost any landscape. But the truly horrifying feature is the sideways rain of molten glass. The intense radiation from the star vaporizes silicate particles in the planet's upper atmosphere. These particles then condense into microscopic shards of glass, which are swept across the planet's surface by the supersonic winds. Unlike rain on Earth, which nourishes life, these glass particles lash the surface horizontally, creating conditions that are unimaginably violent and lethal. The planet is essentially a global forge of destruction, its atmosphere a furnace where even basic chemical structures struggle to survive. The physics behind this deadly phenomenon is both fascinating and terrifying. The star emits vast amounts of ultraviolet and X-ray radiation, energizing the atmosphere of Glass Rainmaker to extreme levels. The upper layers heat rapidly, creating violent convection currents and supersonic wind patterns. Silicates and other heavy elements in the atmosphere are vaporized at temperatures exceeding 2,000 degrees Celsius, then carried by the wind until they condense into glass particles. These particles are then hurled across the planet's surface at tremendous speeds, creating a sideways rain that no life could withstand. The environment is a perfect illustration of how a relatively normal star, under the right conditions, can transform its nearby worlds into death traps. What makes this star especially noteworthy is the contrast between its relatively mundane appearance and the extreme effects it has on its planet. From a distance, the star might seem harmless, a steady point of light in the night sky. Yet for Glass Rainmaker, it is the architect of perpetual chaos. Unlike pulsars or magnetars, this star doesn't need violent flares or exotic physics to wreak havoc. Its mere proximity and constant radiation output are enough to maintain an uninhabitable environment, proving that even ordinary stars can create extraordinary hazards under the right circumstances. The star's influence on Glass Rainmaker also provides a remarkable insight into atmospheric physics under extreme conditions. Observations of the planet's atmosphere have revealed variations in wind patterns, heat distribution, and chemical composition that challenge our models. For instance, the planet's day side is scorched to thousands of degrees, while the night side, although cooler, is still hostile beyond comprehension. The relentless stellar bombardment ensures that any molecules or potential life forms are instantly destroyed, effectively sterilizing the planet. In this sense, Glass Rainmaker is a cautionary tale about how planetary environments can be shaped and obliterated by their stars. Beyond the scientific fascination, the star-planet system evokes a sense of cosmic horror. The idea that a world can literally have glass raining sideways across its surface, driven by a star's unyielding radiation, stretches our imagination. It is a reminder that the universe is not designed for life in most places. Instead, it is a theater of extremes, where stars can act as both creators and destroyers. Glass Rainmaker, with its relentless sideways glass storms, embodies the lethal power that even a seemingly ordinary star can exert over its planetary companions. This star also illustrates how close-orbiting exoplanets are particularly vulnerable. Unlike Earth, which orbits at a safe distance from the Sun, Glass Rainmaker's tight orbit exposes it to constant danger. Tidal locking likely keeps one side of the planet perpetually facing the star, baking it continuously, while the other side remains in a near-constant night, swept by violent winds carrying molten particles. In essence, the planet is trapped in a never-ending cycle of destruction, a world that exists only as a testament to the star's unrelenting power. For astronomers, the system is a treasure trove of extreme physics. By studying how this star interacts with its planet, scientists can better understand atmospheric dynamics under high radiation, wind patterns at extraordinary speeds, and how planetary chemistry behaves under conditions far beyond earthly experience. For everyone else, however, the nickname Glass Rainmaker perfectly captures the horror and majesty of a world where even the air is lethal, shaped entirely by the star's relentless fury. SN 1987, A's progenitor, the Supernova Blueprint. This star stands as one of the most historically significant and terrifying stellar objects ever observed. It is the progenitor of one of the closest and most studied supernovae in modern times, a cosmic event that shocked astronomers and illuminated just how destructive stellar explosions can be. Located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, this star met its end in a supernova in 1987, producing an explosion visible to the naked eye from Earth. The brilliance of this supernova briefly outshone an entire galaxy segment, releasing more energy in a matter of weeks than the Sun would emit over its entire 10 billion-year lifetime. Its death not only reshaped its surroundings, but provided an unprecedented opportunity to observe stellar death in real time, making it a blueprint for understanding catastrophic cosmic events. Before its demise, this star was a massive blue supergiant, much hotter and more luminous than our Sun. Its size and temperature made it a ticking time bomb. Massive stars like this exhaust their nuclear fuel rapidly, fusing lighter elements into heavier ones until an iron core forms. Iron fusion absorbs energy instead of producing it, leading to a catastrophic collapse of the core under the star's own gravity. The sudden implosion triggers an enormous rebound effect. Outer layers are blasted into space at tens of thousands of kilometers per second, creating a supernova capable of outshining billions of stars for a short period. This star, through its explosion, vividly demonstrated this process, giving humanity a real-world glimpse of stellar annihilation in action. The supernova unleashed by this star was not just a spectacle of light. It was an immense release of matter and radiation, shaping the surrounding cosmic environment. Shockwaves from the blast swept through nearby interstellar material, compressing gas clouds and potentially triggering new star formation, while simultaneously obliterating any pre-existing structures in its immediate vicinity. The expelled material, rich in heavy elements such as oxygen, silicon, and iron, seeded the cosmos with the building blocks for future planets and life. A violent yet necessary process in the cycle of cosmic evolution. In this sense, the star's death was both destructive and creative, a paradoxical reminder of the duality of stellar life cycles. One of the most haunting aspects of this star's demise is its proximity to Earth. Although 168,000 light-years may sound distant, it is remarkably close on a cosmic scale. The explosion was powerful enough that neutrinos, ghostly particles produced in vast quantities during the core collapse, were detected on Earth, offering the first direct confirmation of supernova theories. The energy released in neutrinos alone exceeded the total energy radiated in visible light, providing a terrifying measure of the raw power these stars can unleash. In a universe populated with such massive stars, it is sobering to consider that similar events could occur within our own galaxy, close enough to pose a genuine threat to life if the conditions were right. The progenitor star's supernova also revealed the long-term effects of such stellar explosions. Decades after the initial blast, astronomers continue to observe its remnants, a spectacular ring of glowing gas illuminated by the shockwave. These remnants are a haunting reminder of the star's final act, a cosmic scar that will persist for tens of thousands of years. The material is still expanding, and its interaction with the surrounding medium creates complex shock structures and radiation, effectively acting as a laboratory for studying extreme astrophysics. It is an enduring testament to how violent and far-reaching a star's death can be. Scientifically, this star became a milestone in supernova studies. Prior to its explosion, most of what we knew about massive star death came from theoretical models and distant observations. Seeing a supernova occur in a relatively nearby galaxy allowed astronomers to track its evolution in unprecedented detail. From neutrino bursts to the expansion of the debris cloud, this star provided empirical evidence for nuclear processes occurring at stellar cores, the dynamics of shock propagation, and the enrichment of interstellar space with heavy elements. Each observation underscored the destructive potential inherent in stars of this mass, showing that their deaths are not gentle fades, but violent reshaping events that affect entire regions of space. Beyond the scientific fascination, this star embodies the terrifying reality of cosmic mortality. Massive stars live fast and die in spectacularly violent ways, capable of sending lethal radiation and shockwaves across unimaginable distances. The progenitor star's supernova was a cosmic firework visible from Earth, a reminder that the universe is far from static. While humanity observes these events safely, they serve as a warning. The life of massive stars is a countdown to explosive destruction, and the forces they unleash dwarf anything we can imagine on a planetary scale. The very fabric of space can be scarred, planets can be obliterated, and new stars can be born, all as a result of a single star's death. In essence, this star is the archetype of stellar destruction, a living, or rather, once living, blueprint for the power and unpredictability of massive stars. It shows how the universe recycles matter with catastrophic efficiency, turning violent death into the seeds of new creation. Observing its explosion provided both awe-inspiring beauty and a stark lesson in cosmic danger, emphasizing that while stars may twinkle peacefully from a distance, their ultimate fates can unleash forces capable of reshaping galaxies. PSR J1903+0327. The Impossible Pulsar. This star stands out among the most perplexing and unsettling stellar objects ever discovered because it challenges fundamental assumptions about how pulsars form and behave. Known as the Impossible Pulsar, it exists in an orbit that defies conventional models of stellar evolution. Most pulsars, which are rapidly spinning neutron stars, are found either in isolation or in binary systems with companion stars that fit specific evolutionary scenarios. Yet this star exhibits an orbital pattern that seemed impossible for decades. It is in a highly eccentric orbit around a Sun-like companion, a configuration that contradicts the expectations set by standard astrophysics. For scientists, this star is not only fascinating, but also a reminder that the universe does not always follow the rules we believe govern it. The Impossible Pulsar spins at a remarkable speed of about 465 times per second, which already places it among the fastest known pulsars, though not as extreme as some millisecond pulsars. What is more astonishing, however, is the nature of its companion and the highly elliptical orbit. Most millisecond pulsars achieve their rapid spins by accreting matter from a companion star in a tight circular orbit. That process both spins up the pulsar and stabilizes the orbit over time. Yet in this system, the orbit remains unusually stretched, suggesting that the star somehow acquired its high rotational velocity without the usual tidal and mass transfer interactions. The puzzle has baffled astronomers since its discovery, earning it the nickname Impossible Pulsar for its seeming violation of well-established formation rules. From a danger standpoint, this star is less immediately lethal than magnetars or gamma-ray burst progenitors, but it is still a deadly object by nature. As a pulsar, it emits powerful beams of electromagnetic radiation from its magnetic poles. If any planet or object were to cross the path of these beams, it would be subjected to intense radiation capable of stripping atmospheres and irradiating surfaces. Though the beams are not aimed at Earth, the principle remains the same. This star is a precise and relentless emitter of high-energy particles. Its very existence demonstrates the extremes to which neutron stars can be pushed by the laws of physics and gravity. The impossible pulsar also provides crucial insights into stellar dynamics, gravity, and relativity. The eccentric orbit allows astronomers to test general relativity under conditions that are not present in most binary systems. Tiny perturbations in the orbit and timing of its pulses offer clues about the gravitational interaction between massive, dense objects. The star becomes a natural laboratory, teaching us not only about pulsars themselves, but also about the fundamental rules of spacetime. Yet this scientific value comes with an underlying sense of cosmic unease. Here is a star that refuses to follow the script of the universe, defying our expectations in ways that hint at hidden complexities in stellar formation and evolution. Adding to the star's mystique, its formation history is deeply puzzling. One leading theory suggests that it was once part of a triple system, where dynamic interactions ejected one star and left the pulsar in an eccentric orbit with a companion it should not have had. Such a chaotic birth scenario underscores the unpredictable nature of the universe, showing that even stars we think we understand can emerge in configurations that appear impossible. Unlike the steady, predictable motion of most celestial bodies, this star embodies unpredictability and the chaotic potential of stellar dynamics. In terms of observation, this star is relatively faint in visible light, its presence primarily detectable through radio telescopes that pick up its regular pulses. These pulses are like cosmic clockwork, arriving with astonishing precision, yet the system's orbital eccentricity introduces variations that intrigue scientists and continue to inspire new research. Every pulse carries encoded information about its orbit, spin, and environment, turning the impossible pulsar into a cosmic data beacon that is both fascinating and unsettling in its implications. The impossible pulsar reminds us that even in the structured cosmos, there are exceptions that challenge our understanding. It is a testament to nature's ability to produce not only beauty and order, but also anomalies that defy expectation. While it may not have the immediate destructive power of a magnetar or a gamma-ray burst progenitor, the star's bizarre orbit, extreme spin, and precise radiation beams make it a formidable and enigmatic presence in the galaxy. It is a warning that even objects that seem well understood can harbor secrets capable of rewriting scientific rules, and that the universe often has surprises lurking just beyond the edge of what we think is possible. 13601, the star that shouldn't exist. This star is the epitome of cosmic extremity, earning the nickname the star that shouldn't exist, because it defies nearly every expectation astrophysicists have about stellar formation and stability. Located in the heart of the Tarantula Nebula, within the Large Magellanic Cloud, this star is a true behemoth. With an estimated mass over 250 times that of the Sun and luminosity millions of times greater, it pushes the boundaries of what we understand about how stars form and survive. In simpler terms, the very existence of this star seems almost impossible according to classical models of stellar physics. Gravity, radiation pressure, and the mechanisms of nuclear fusion should destabilize a star of this magnitude. Yet it not only exists, it thrives, burning with an intensity that is almost incomprehensible. The star's incredible mass makes it profoundly unstable. Massive stars generate enormous amounts of energy through nuclear fusion, which in turn produces radiation pressure, pushing outward against gravity. For most stars, this balance is delicate but sustainable. In the case of this star, the outward radiation pressure is so extreme that it should blow the star apart entirely. The fact that it has survived, even for a few million years, a fraction of the Sun's 10 billion-year lifespan, is a testament to the delicate and extreme physics at play. Its instability also manifests in violent stellar winds, which carry away mass at millions of tons per second. These winds are so intense that the star is gradually shedding its outer layers, a slow-motion cosmic unraveling that underscores just how precarious its existence is. The destructive potential of this star is staggering. Were a star of similar magnitude to exist anywhere near Earth, it would outshine the entire night sky, and its intense radiation would strip away atmospheres and sterilize surfaces on any nearby planets. Its stellar winds themselves are deadly on a cosmic scale, pushing and heating the surrounding interstellar medium, triggering shock waves that can compress gas clouds and catalyze the formation of other massive stars, or obliterate nascent planetary systems before they can form. This star is essentially a supernova in waiting, a ticking time bomb of nuclear fusion and gravitational tension poised to explode in a hypernova that would dwarf typical supernova. One of the most intriguing aspects of this star is its potential fate. The most massive stars are believed to end their lives in either direct collapse to black holes or in hypernovae that emit gamma-ray bursts capable of sterilizing entire planetary systems across vast distances. Given its extraordinary mass and instability, this star is a prime candidate for such an explosive end. Scientists predict that when it finally reaches the end of its life, the explosion could release more energy in seconds than the Sun will emit over its entire lifetime. The surrounding nebula would be obliterated, shock waves would ripple across interstellar space, and any planets within dozens or even hundreds of light years could be annihilated. In essence, the star is not only defying physics now, it is setting the stage for a catastrophic finale that could have repercussions across the galaxy. The star's extreme temperature and brightness add to its monstrous character. Its surface temperature exceeds 50,000 degrees Celsius, nearly 10 times hotter than the Sun. Such heat generates intense ultraviolet radiation, which sculpts the surrounding gas clouds, creating visually stunning but deadly stellar environments. This radiation also drives powerful stellar winds, stripping material from the star and injecting enormous energy into the Tarantula Nebula. These interactions shape the star's neighborhood in ways that are both beautiful and terrifying, creating cosmic landscapes that are simultaneously formative and destructive. Astrophysicists study this star not only to understand stellar formation at extreme masses, but also to probe the limits of physics. Its existence challenges models of how radiation pressure limits star size, how mass loss occurs in the most massive stars, and how nuclear fusion can proceed stably under such extreme conditions. Every observation forces scientists to reconsider the upper limits of stellar mass, the efficiency of nuclear burning, and the mechanisms that allow such a star to exist without disintegrating immediately. In other words, this star is a living laboratory of extreme physics, showing us what is possible when nature operates at the very edge of comprehension. Beyond science, the star evokes awe and dread. It is a luminous leviathan, a celestial anomaly whose mass and energy dwarf any familiar reference point. While it appears as a point of light from our vantage, its internal processes are nothing short of cataclysmic. It embodies the idea that the universe can create objects so extreme that they seem almost unnatural, objects that exist on the razor's edge between stability and destruction. The star's very existence is a challenge to human understanding, a cosmic reminder that the universe is capable of producing phenomena far beyond our imagination. IGR J1901-3624-, the mini black hole. Mimic. This star is a cosmic enigma, earning its nickname, the mini black hole mimic, because it exhibits behaviors normally reserved for the universe's most feared objects, black holes. Yet it is far smaller and less massive than typical black holes. Located in the Milky Way, this star is an X-ray binary system, where a compact object, likely a neutron star or a stellar mass black hole candidate, siphons matter from a companion star. What makes it terrifying is the violent variability of its X-ray emissions, which mimic the erratic, near-apocalyptic outbursts typically associated with black hole accretion disks. Its pulses and flares are intense, unpredictable, and capable of unleashing vast amounts of energy into the surrounding space, creating a miniature but highly destructive analogue to a full-sized black hole. The most famous characteristic of this star is its heartbeat oscillation pattern, a phenomenon observed in its X-ray light curve. Unlike most neutron stars or smaller stellar remnants, which emit steady or predictable radiation, this star produces rhythmic bursts of energy that resemble the violent feeding frenzies seen around black holes. Each burst is a violent episode of mass transfer and energy release, where material from the companion star is torn apart, accelerated to near light speed, and ejected with enormous energy. The cycle repeats with astonishing regularity, sometimes over periods of tens of seconds, giving the star a living, pulsing presence. To any hypothetical observer on a nearby planet, these outbursts would be catastrophic, exposing the surface to lethal X-rays and gamma rays. The physics behind the mini black hole mimic's behavior is both fascinating and terrifying. Matter falling onto the compact object forms an accretion disk, which heats up to millions of degrees due to friction and gravitational compression. In typical black holes, material crosses the event horizon and disappears from the observable universe. Here, even if the central object is not a true black hole, the intense gravity and rotation create similar energetic outbursts. The star's size may be smaller, but its ability to release concentrated energy rivals that of some of the most massive stellar systems, effectively producing miniature cosmic explosions on a recurring basis. Its heartbeat is both a signal of life and a warning of imminent danger, a reminder that even smaller stellar remnants can act like engines of destruction. Beyond its flares, the star's environment is highly unstable. The companion star is slowly being stripped of material, contributing to the violent variability of the system. This process is a vivid demonstration of stellar cannibalism. One star feeds on another, generating catastrophic energy releases that ripple through space. Any planetary bodies nearby would not stand a chance. The constant radiation, violent winds, and ejected matter create an inhospitable zone extending light years from the system. This star is a predator in microcosm, showing how extreme physics can replicate black hole-like phenomena on a smaller scale, but with effects that are no less deadly. Another remarkable aspect of this star is its comparative size versus impact. While typical black holes are feared because of their immense mass and ability to distort space-time, this star demonstrates that size alone is not the measure of danger. By leveraging accretion dynamics and extreme rotation, it can generate enormous energy releases without requiring the mass of a full-fledged black hole. In doing so, it challenges assumptions about stellar danger zones and shows that even smaller objects can produce life-destroying conditions, making it a uniquely terrifying member of the cosmos. Astronomers study this star not just for its dramatic behavior, but also for the insights it provides into extreme physics. By analyzing the timing, intensity, and spectral characteristics of its X-ray emissions, scientists can probe the physics of accretion disks, the behavior of matter under intense gravity, and the mechanics of energy release near compact objects. The star is essentially a scaled-down laboratory for phenomena that are otherwise only observed near black holes, offering a window into cosmic processes that are both beautiful and deadly. The mini black hole mimic also serves as a reminder of the universe's capacity for surprise. It combines the characteristics of multiple extreme objects, a neutron star, a black hole-like accretion system, and a cannibalistic binary, into one entity. Its violent outbursts, rhythmic yet unpredictable, are a testament to the creative and destructive power of gravity, radiation, and stellar interaction. While it may not bend space-time as dramatically as supermassive black holes, its capacity to generate intense, localized destruction is a chilling reminder that danger in the cosmos comes in many forms. In essence, this star exemplifies how small does not mean harmless. Its pulses and flares echo the universe's most violent phenomena, yet on a scale that is more accessible to observation, allowing scientists to study the terrifying physics up close. It is both a mimic and a monster in its own right, proving that, in the cosmos, even stars that appear modest in mass can wield destructive power that rivals the deadliest forces in existence. Zeta Ophiuchi, the runaway star. This star is one of the most dramatic and violent travelers in the cosmos, earning the evocative name the runaway star due to its extraordinary speed and destructive influence on the interstellar medium. Hurtling through space at over 20 miles per second, roughly 72,000 kilometers per hour, this star is effectively a cosmic bullet, leaving a trail of devastation in its wake. Its journey through the galaxy is not leisurely. The sheer velocity combined with its immense mass generates powerful shock waves that compress, heat, and stir the surrounding interstellar gas, creating turbulent zones that can trigger new star formation or obliterate nascent planetary systems. The destructive potential of Zeta Ophiuchi lies not in explosions or radiation alone, but in the kinetic energy it carries across light years of space. The star's velocity is the result of a violent past. Zeta Ophiuchi is believed to have been part of a binary system, paired with a massive companion that eventually went supernova. The explosion violently ejected the surviving star at incredible speed, effectively making it a runaway. This violent ejection transformed it from an ordinary massive star into a high-speed interstellar predator. As it moves, its powerful stellar winds, streams of charged particles flowing outward at millions of kilometers per hour, plow into the surrounding interstellar medium. These winds, combined with its motion, create bow shocks ahead of the star, similar to the wave formed at the prow of a speeding ship, compressing gas and dust into intricate, sometimes spectacular formations. Observations reveal glowing arcs of ionized gas tracing the star's path, a visual testament to the cosmic havoc it creates. What makes this star particularly terrifying is that its speed and mass combine to produce a unique and relentless form of destruction. While stationary massive stars can affect their surroundings through radiation and occasional supernovae, Zeta Ophiuchi is continuously carving a path of chaos. The shock waves generated by its motion heat interstellar gas to tens of thousands of degrees and accelerate particles to relativistic speeds. Any smaller objects in its trajectory, rogue planets, asteroids, or even gas clouds, face violent collisions or complete dispersal. The star's movement effectively reshapes its local environment, acting as a living, moving agent of cosmic destruction. The star's sheer mass and luminosity also amplify its danger. As an O-type star, it is tens of times more massive than the Sun and tens of thousands of times more luminous. This produces intense ultraviolet radiation that ionizes the gas in its vicinity, creating a vast region of plasma surrounding its path. Combined with its bow shock, Zeta Ophiuchi is not merely moving through space. It is actively sculpting it, leaving visible trails that highlight both the destructive and transformative power of massive stars. Its environment becomes a turbulent, glowing testament to extreme astrophysics in action. Another fascinating aspect of Zeta Ophiuchi is its influence on star formation. While it can obliterate fragile structures in its path, the compression of interstellar gas in the bow shock can also trigger new stars to form. In this sense, it embodies the duality of cosmic destruction and creation. It is a stellar bulldozer, a high-speed sculptor reshaping the galaxy, demonstrating that stars are not passive points of light, but dynamic forces capable of remolding the interstellar medium over light years. Its motion provides real-time insight into the interaction between massive stars and the galaxy, revealing processes that usually occur over millions of years. Zeta Ophiuchi's runaway status also gives it a unique observational signature. The combination of high-speed motion, strong stellar winds, and intense ultraviolet radiation makes it an ideal object for studying bow shocks, stellar feedback mechanisms, and the interplay between massive stars and their environments. Its trajectory and speed allow astronomers to trace its violent history, reconstructing the supernova that propelled it and mapping the trail of interstellar turbulence it leaves behind. These observations not only help us understand this star, but also offer a window into the life cycles of massive stars, the dynamics of binary systems, and the mechanisms of galactic evolution. In essence, Zeta Ophiuchi is a living warning of the dynamic, often violent nature of the universe. It is not stationary, passive, or predictable. It is a high-speed marauder, carrying energy and mass across the galaxy, reshaping interstellar space, and demonstrating that danger in the cosmos comes not only from explosions or radiation, but also from relentless motion. For any nearby systems unfortunate enough to lie in its path, this star is a destroyer, a cosmic force that shows how even a single high-speed star can influence and potentially devastate its galactic neighborhood. PSR J2144-3933 the longest period pulsar. This star is one of the most confounding and unsettling pulsars ever discovered, earning its place in astrophysics as a true outlier. Known as the longest period pulsar, it pulses every 8.5 seconds, an interval that seems almost leisurely compared to typical pulsars, which often rotate dozens or hundreds of times per second. At first glance, this slow rhythm may appear harmless or unremarkable, but in reality, it violates our fundamental understanding of how pulsars operate and survive. Pulsars are neutron stars, incredibly dense remnants of supernova explosions, and their magnetic fields drive emissions that sweep across space like cosmic lighthouses. Conventional models predicted that pulsars with such slow rotation should have already ceased emitting detectable radiation, having lost too much energy to continue their pulsing activity. Yet this star persists, a defiant anomaly in the universe, challenging the established physics of neutron stars. The very existence of this star forces astronomers to reconsider the limits of pulsar lifespans. Normally, as pulsars age, their rotational energy diminishes, and they eventually cross what is known as the death line, a threshold beyond which the magnetic field is no longer capable of accelerating particles to produce detectable radio emissions. The longest period pulsar, however, continues to generate pulses despite its slow spin, implying either an unexpected internal mechanism that sustains its emissions or that our understanding of the death line is incomplete. Its persistent pulsing at such a leisurely pace is a cosmic anomaly, a stubborn heartbeat that refuses to fade despite the odds. This makes the star both scientifically fascinating and eerily defiant, a celestial object that refuses to obey the rules we thought were universal. The physics underlying this star is equally perplexing. Its magnetic field, though weaker than that of younger, faster pulsars, is still strong enough to accelerate charged particles along magnetic field lines, producing detectable radio emissions. However, the emission mechanisms at such slow rotational periods are poorly understood. The star may be emitting through exotic processes, potentially involving a complex interplay of residual magnetic energy, crustal movements, or interactions between the magnetic field and the surrounding plasma. Each pulse it sends across the cosmos is a tiny but persistent reminder of how even the remnants of dead stars can defy expectations and retain lethal potential. In a hypothetical nearby system, the star's emissions could irradiate planets or smaller bodies, though the intensity would be far less immediately deadly than a magnetar or gamma-ray burst source. Nevertheless, its persistence at slow speeds underscores a form of cosmic resilience that is both awe-inspiring and unsettling. Observationally, this star offers a rare laboratory for studying the later stages of neutron-star evolution. Pulsars with such slow periods are incredibly difficult to detect because their pulses are weak and infrequent compared to their rapidly spinning counterparts. That astronomers were able to identify and track this star is a testament to modern radio astronomy and sophisticated signal processing techniques. Each observation of its pulses provides invaluable data about neutron-star magnetic fields, particle acceleration, and the long-term evolution of compact objects. Moreover, the star challenges models of pulsar populations, suggesting that many slow, undetected pulsars may exist, silently pulsing in the galaxy, hidden from conventional observation. These hidden populations could hold the key to understanding the full life cycle of neutron stars. The star's anomalous behavior also carries broader implications for astrophysics. It forces a reconsideration of the magnetic field decay rates, energy loss mechanisms, and emission processes of neutron stars. Its continued activity at such a slow rotation period suggests that neutron stars may be capable of far more diverse behaviors than previously thought. The discovery of this star is a reminder that even in the highly studied field of pulsar physics, nature can produce objects that defy prediction, highlighting the limits of human understanding in the face of the cosmos's vast complexity. In a more philosophical sense, this star embodies the persistence of cosmic structures against the odds. While most neutron stars either spin rapidly or gradually fade into undetectability, this star maintains its presence as a slow, measured heartbeat. Its 8.5-second pulses are a reminder that the universe is full of anomalies that challenge our assumptions, teaching us humility in the face of cosmic forces. It is a slow-moving, persistent monument to the unexpected, demonstrating that even the remnants of dead stars can continue to wield influence across light years. Eta Carinae, the supernova in waiting. This star is arguably one of the most dangerous and awe-inspiring objects in our galaxy, earning its terrifying nickname, the supernova in waiting. Located roughly 7,500 light-years from Earth in the Carinae constellation, it is a massive stellar system that has long fascinated and unsettled astronomers. Eta Carinae is actually a binary system composed of two colossal stars locked in a gravitational dance. The primary is a luminous blue variable, LBV, with an estimated mass of 100 to 150 times that of the Sun, and the secondary, though smaller, is still a massive and highly energetic star. Together, they create a volatile system characterized by extreme luminosity, unstable stellar winds, and unpredictable outbursts. The sheer scale of this system is staggering. It radiates over 5 million times the energy of the Sun, and its mass is so great that it defies conventional expectations of stellar stability. The primary star in the Eta Carinae system has a history of violent behavior, with the most famous event being the Great Eruption in the 19th century. Between 1837 and 1858, the star experienced a colossal outburst that briefly made it the second brightest star in the night sky, rivaling Sirius. During this period, Eta Carinae expelled an estimated 10 to 20 solar masses of material, creating the stunning homunculus nebula that now surrounds it. This eruption released an enormous amount of energy, equivalent to hundreds of millions of times the annual output of the Sun, and reshaped the surrounding interstellar medium. The scale and violence of this outburst were enough to demonstrate that this system is capable of releasing catastrophic energy without yet reaching its ultimate supernova event. The nebula itself is a haunting monument to the destructive power of massive stars, a twisted and glowing testament to the star's volatility. What makes Eta Carinae particularly terrifying is its potential to end its life as a hypernova, one of the most luminous and energetic types of supernovae in the universe. Unlike typical supernovae, which release energy on the scale of 10 to the 44th power joules, hypernovae can produce 10 to 100 times more energy, accompanied by massive gamma-ray bursts capable of sterilizing planets over thousands of light years. While Earth is far enough away to avoid immediate destruction, the cosmic scale of Eta Carinae's potential explosion is difficult to overstate. A hypernova from this system would briefly outshine entire galaxies, bathing nearby star systems in lethal radiation. For planets within a few thousand light years, the event could strip atmospheres, destroy ozone layers, and potentially extinguish life. Its future death is a ticking cosmic clock, and while it might not occur for tens of thousands of years, the scale of the possible devastation is staggering. The system's volatility is further amplified by the binary interaction. The secondary star orbits the primary in a highly elliptical orbit, periodically plunging through regions of extremely dense stellar wind from the primary. These close encounters generate massive shockwaves and can trigger additional outbursts of material. The interaction of the two stars' stellar winds creates regions of incredible pressure and temperature, producing X-rays and high-energy radiation detectable across vast distances. These violent interactions continually reshape the nebula and surrounding space, making Eta Carinae a laboratory for extreme stellar physics. Observations of these winds and outbursts have revealed that the system is far from stable, with the potential for a massive eruption at any time, a smaller-scale warning of the hypernova that eventually awaits. Another element that contributes to Eta Carinae's terror is the nature of massive star evolution. Stars this large burn through their nuclear fuel at extraordinary rates, fusing elements rapidly and creating massive cores composed of iron and heavier elements. Once the core reaches critical mass, gravity overwhelms the outward pressure, triggering core collapse. Given the primary star's extreme mass, it is likely that this process will culminate not just in a supernova, but in a hypernova, possibly forming a stellar mass black hole. The binary nature of the system complicates predictions, as gravitational interactions could influence the timing and symmetry of the explosion. Astronomers monitor Eta Carinae closely, because even slight asymmetries in the collapse could focus energy in specific directions, creating concentrated beams of gamma rays or relativistic jets, a nightmare scenario for any nearby star systems. Eta Carinae's sheer luminosity adds another layer to its awe-inspiring danger. The star emits vast quantities of ultraviolet radiation, ionizing surrounding gas and creating glowing nebulae visible across thousands of light years. The homunculus nebula, sculpted during past eruptions, contains bipolar lobes and dense gas clouds that continue to interact with the star's radiation and winds. the energy and mass ejected by Eta Carinae affect star formation in its vicinity, compressing gas in some areas, while obliterating protoplanetary clouds in others. Its influence extends far beyond its immediate location, demonstrating that even before its ultimate demise, Eta Carinae is a destructive powerhouse. For scientists, the system is a treasure trove of extreme physics. It provides real-world data on the life cycle of the most massive stars, the behavior of luminous blue variables, the mechanics of binary interactions, and the triggers for massive outbursts. Its study has refined models of stellar wind collision, radiation-driven mass loss, and the evolution of massive binary systems. At the same time, its unpredictability is a sobering reminder that nature does not always follow human expectations. Eta Carinae is a living warning that extreme mass and energy can combine to produce objects capable of reshaping the galaxy, even without exploding. V838 Monocerotis, the star that swelled and died. This star is one of the most enigmatic and visually spectacular objects in the universe, earning the haunting nickname, the star that swelled and died, because of its bizarre and violent behavior observed in the early 21st century. Unlike typical supernovae or variable stars, this star's eruption in 2002 defied expectations, producing a sudden, dramatic expansion that caused it to brighten by a factor of hundreds of thousands in just a few weeks. The event was not a conventional explosion that destroyed the star immediately. Rather, it was an unpredictable swelling that ejected massive amounts of material into space while leaving the core intact. What makes this star truly terrifying is that its outburst generated a light echo, an expanding reflection of light bouncing off surrounding dust clouds, illuminating the interstellar environment in an eerily beautiful yet deadly display. This ghostly light echo revealed the violent dynamics of the star's eruption while visually demonstrating the sheer scale of the energy it released. The eruption of this star was not only visually stunning, but physically extreme. During the outburst, the star expanded to a radius thousands of times larger than the Sun, enveloping any hypothetical nearby planets in an inferno of superheated gases and radiation. The luminosity of the star increased dramatically, releasing energy that temporarily outshone the combined light of its surrounding stellar neighborhood. Observations showed that the ejected material traveled at hundreds of kilometers per second, carrying enough mass and energy to disturb nearby interstellar gas clouds. This violent ejection of matter demonstrates the star's capacity to sculpt its environment on a galactic scale, turning ordinary regions of space into turbulent, high-energy zones. In effect, the star became both a creator and a destroyer, producing dazzling beauty while simultaneously exhibiting deadly astrophysical violence. One of the most fascinating and terrifying aspects of this star is the light echo itself. Light echoes occur when intense bursts of light from a star illuminate surrounding dust at varying distances, creating concentric shells of reflected light that appear to expand over time. In this case, the echo of the star's eruption formed a multi-layered, three-dimensional visual spectacle, giving astronomers a rare glimpse of the structure of the surrounding interstellar medium. Yet this beauty conceals a violent truth. The expanding shells of dust were propelled and heated by the star's outburst, carrying kinetic energy capable of influencing nearby molecular clouds and potentially destabilizing protoplanetary systems. The interplay between radiant energy, ejected material, and dust clouds demonstrates the terrifying influence even a single, non-supernova star can have on its surroundings. The underlying cause of this star's dramatic eruption remains a topic of intense study and speculation, adding to its mysterious and frightening character. Some theories suggest that the swelling resulted from a stellar merger, where two stars collided and combined, releasing enormous energy in the process. Others propose that the star underwent a rare and violent phase of internal instability, where sudden shifts in nuclear fusion processes forced the star to expand rapidly. Whatever the mechanism, the eruption defied conventional astrophysical models, challenging scientists' understanding of how massive stars behave in their late evolutionary stages. This unpredictability makes the star a cosmic wildcard, a reminder that the universe can produce explosive phenomena even in stars that are not yet nearing total collapse. The star's violent past and potential for future instability make it a particularly chilling object. Even after the 2002 eruption, the star remains highly luminous and unstable, with residual mass ejections continuing to interact with surrounding dust and gas. These ongoing processes suggest that the star could experience additional eruptions or shifts in luminosity, each capable of generating further light echoes and releasing dangerous energy into the surrounding environment. Unlike a classical supernova, which annihilates a star and leaves behind a compact remnant, this star demonstrates that instability and destruction can manifest in other, equally violent ways. Its ability to release enormous amounts of energy without complete destruction is a rare and terrifying form of stellar behavior, showing that cosmic danger comes in more forms than one might expect. Astronomically, this star offers invaluable insight into stellar evolution, the behavior of luminous red variables, and the dynamics of massive star envelopes. Observations of its eruption, expansion, and light echo have provided unprecedented data about the interaction between stellar outbursts and surrounding interstellar matter. These insights help astronomers understand the life cycles of massive stars, the formation of nebulae, and the mechanisms by which stars influence their galactic environments. Yet, while scientifically illuminating, the star's behavior also underscores the raw and unpredictable power inherent in massive stellar objects, illustrating how even relatively nearby stars can produce sudden, violent phenomena that alter their surroundings dramatically. Philosophically, the star that swelled and died embodies the terrifying duality of cosmic creation and destruction. Its eruption produced breathtaking beauty, a luminous spectacle visible across vast distances, yet that beauty was inseparable from deadly energy and violent forces. For hypothetical observers or planets in proximity, the star's eruption would have been catastrophic, a lethal reminder that the cosmos is not only awe-inspiring, but profoundly dangerous. It is a living example of how stellar processes, while governed by physics, can produce outcomes that are unpredictable, extreme, and potentially lethal. In summary, this star is a cosmic paradox, a star that grew enormously, ejected massive amounts of matter, and created hauntingly beautiful light echoes, all while demonstrating the capacity for deadly energy release. Its behavior challenges conventional astrophysical theory, forces scientists to reconsider models of stellar instability, and reminds us that the universe contains objects whose beauty is inseparable from their potential for destruction. The star that swelled and died is not just a visual wonder. It is a terrifying illustration of the unpredictable, violent, and awe-inspiring forces that govern the night sky. It teaches that in the cosmos, appearances can be deceiving. What captivates the eye may simultaneously threaten existence on a cosmic scale. Swift J1644+57. The star-eating black hole event. This star is one of the most horrifying examples of cosmic annihilation, earning its chilling nickname because it was literally consumed by a black hole in a catastrophic tidal disruption event. Unlike typical stars that live out their lives over millions or billions of years, this star met a violent and instantaneous fate, ripped apart by the immense gravitational forces of a supermassive black hole. Located hundreds of millions of light-years away, the star's encounter with the black hole triggered a cataclysmic sequence of events, converting its mass into an extraordinarily energetic outburst that unleashed deadly radiation across the surrounding galaxy. This star is a stark reminder that in the universe, proximity to the wrong cosmic object can result in total annihilation, with no warning and no chance of escape. The physics behind this event is as fascinating as it is terrifying. As the star approached the black hole, gravitational tidal forces became exponentially stronger than the star's own self-gravity. These forces stretched the star along the direction toward the black hole while compressing it perpendicularly, effectively shredding it into streams of stellar material. Some of this material was flung away at relativistic speeds, while the rest spiraled inward, forming an accretion disk around the black hole. This sudden influx of mass into the black hole's disk released enormous amounts of energy, primarily in the form of X-rays and gamma rays. Observatories detected these emissions as intense, long-lasting flares, which at their peak could have outshone the galaxy in which the event occurred. For any hypothetical planet near the line of the radiation, the exposure would have been instantly lethal, bombarding surfaces with deadly high-energy photons capable of stripping away atmospheres and irradiating matter at a fundamental level. What makes this star particularly terrifying is that its destruction was not a quiet implosion, but a violent cosmic fireworks display. As the black hole consumed the star, relativistic jets were produced along the black hole's rotational axis, shooting energy at nearly the speed of light into interstellar space. These jets concentrated the star's annihilation energy into narrow, focused streams, effectively creating death beams that could irradiate regions far beyond the black hole's immediate surroundings. Observers from Earth detected these emissions as a prolonged, highly energetic X-ray flare lasting for weeks, a rare and striking example of a tidal disruption event that demonstrates both the destructive power of black holes and the vulnerability of stars that wander too close. The star, once a massive and living entity, was transformed entirely into energy and radiation, a process that is as scientifically invaluable as it is terrifying to contemplate. Beyond its violent end, this star also reshaped the understanding of stellar dynamics near supermassive black holes. Prior to events like this, astronomers had theorized about tidal disruption events, but this star provided direct observational evidence of the process in action. The extreme variability of the resulting radiation, the structure of the emitted jets, and the energy scales involved offered unprecedented insight into both stellar physics and black hole mechanics. The star's death allowed scientists to study how material behaves in the most extreme gravitational environments, how energy is converted from matter in catastrophic events, and how galaxies can be illuminated by sudden bursts of concentrated radiation. While these insights are invaluable for astrophysics, they also underscore the nightmarish reality that stars are fundamentally vulnerable to cosmic predators, and that black holes are capable of transforming life-giving matter into raw, lethal energy. The scale of the destruction is almost impossible to comprehend. The star's mass, once measured in units comparable to our Sun, was effectively transformed into a flood of high-energy radiation in a matter of days. This conversion demonstrates one of the universe's most terrifying principles. A black hole can extract nearly the entire mass energy of a star, concentrating it into a few narrow jets, or emitting it as radiation with devastating intensity. If a star like this were to meet a similar fate within our galaxy at a dangerous distance, the consequences would be catastrophic for any life or planetary system exposed to the jets. Even without a direct hit, the radiation could strip atmospheres, ignite chemical reactions, and alter planetary climates irreversibly. The star-eating black hole event is a chilling example of how cosmic annihilation can occur not only through explosive death, but also through systematic, irresistible consumption by gravity. The event also carries profound philosophical implications about the fragility of stars and planetary systems in the universe. Unlike supernovae, which follow a predictable life cycle based on internal stellar physics, tidal disruption events are entirely contingent on orbital dynamics and proximity. A star may exist peacefully for billions of years, only to be destroyed instantaneously if it strays too close to a gravitational monster. The star-eating black hole event reminds us that danger in the cosmos is not always a slow, predictable process. Some of the universe's most lethal phenomena occur without warning, reshaping our understanding of survival and vulnerability on a galactic scale. It is a vivid demonstration of cosmic power, showing that life, planets, and stars are at the mercy of the universe's most extreme objects. Vela X-1, the vampire star. This star is one of the most sinister stellar objects known, earning the chilling nickname the vampire star because of its relentless gravitational feeding on a companion. Vela X-1 is a massive blue supergiant locked in an intimate binary relationship with a neutron star, an incredibly dense stellar remnant left behind after a supernova. In this deadly pairing, the neutron star acts like a cosmic predator, siphoning material from the supergiant in a violent stellar tug-of-war. The result is a system of extraordinary energy output, dominated by intense X-ray emissions and unpredictable bursts of radiation, creating an environment so hostile that any nearby planets or even minor objects would be utterly obliterated. The vampire star exemplifies the universe's capacity for intricate, ongoing violence, showing that stars do not need to explode to pose an existential threat. The key to the star's terrifying behavior lies in the mechanics of mass transfer. The neutron star's intense gravity pulls streams of matter directly from the surface of the supergiant companion, forming an accretion column that channels this material onto the neutron star's surface. As the gas accelerates under gravity, it reaches phenomenal velocities, heating to millions of degrees and emitting X-rays strong enough to be detected across the galaxy. These emissions are not gentle or uniform. They occur in violent pulses, sometimes resembling mini eruptions, where the inflowing matter ignites on the neutron star's surface. This stellar siphoning transforms the system into a natural X-ray generator of immense power, illuminating the surrounding space with radiation deadly enough to sterilize any nearby planetary surfaces. Vela X-1's orbital dynamics amplify its violent nature. The two stars orbit each other in just over 8 days, a proximity that allows the neutron star to continuously feed from the supergiant. Unlike wider binaries, where mass transfer can be slow or intermittent, this tight orbit guarantees that the siphoning process is nearly constant, creating a persistent zone of high-energy radiation. Moreover, the interaction between the stars produces turbulent stellar winds and shock waves that ripple through space. These winds are composed of ionized gas moving at thousands of kilometers per second, and they collide with the interstellar medium, generating additional high-energy phenomena. The system is, in effect, a permanent laboratory of extreme physics, a living demonstration of gravitational dominance and energetic fury. The consequences of this stellar vampirism are staggering. Over time, the neutron star can strip significant mass from the supergiant, potentially altering the evolution of both stars. This mass loss changes the supergiant's structure, increasing instability in its core and potentially influencing the timing and nature of its eventual supernova. In some scenarios, the neutron star itself could accumulate enough material to collapse further or trigger explosive outbursts. For nearby interstellar objects, this dynamic system is an ongoing hazard, with radiation, stellar winds, and ejected matter creating a lethal environment. The vampire star is not just a one-time threat. It is a persistent agent of cosmic destruction, demonstrating that the danger posed by stars can be continuous rather than episodic. From an observational standpoint, Vela X-1 is a treasure trove of astrophysical insight. Its X-ray emissions provide direct information about accretion physics, magnetic field interactions, and the behavior of matter under extreme gravity. By studying this star, scientists can model the complex interplay between binary companions, understand the mechanisms that trigger high-energy emissions, and probe the limits of neutron-star stability. Each X-ray pulse, each burst of radiation, is a signal of the violent processes at work, offering a rare window into a system where gravity, matter, and energy collide in spectacular and deadly ways. The vampire star also underscores the fragility of stellar balance. While most stars exist in relative isolation, a binary system like this demonstrates that proximity can transform ordinary stellar evolution into a deadly interaction. The neutron star's unrelenting feeding turns the supergiant into a source of both energy and vulnerability. Its X-ray outbursts, while scientifically fascinating, are also a vivid illustration of how interactions in space can create hazards that extend far beyond the individual stars themselves. For any hypothetical observers within the system, or rogue planets in nearby space, the environment would be unimaginably hostile, a landscape of radiation, high-speed winds, and gravitational turmoil. Philosophically, the star embodies a predator-prey relationship writ on a cosmic scale. Unlike explosive supernovae or distant gamma-ray bursts, the vampire star represents a constant, sustained danger, a reminder that some of the universe's deadliest forces are not sudden but ongoing. It is a system of balance and violence, creation and destruction, where two stars' fates are irrevocably intertwined. The neutron star's consumption of its companion is both an elegant example of gravitational mechanics and a horrifying display of natural predation at the stellar level. In essence, Vela X-1 is a cosmic vampire, a system where mass, gravity, and radiation combine to produce an enduring zone of extreme danger. It demonstrates that the universe's terrors are not only the product of isolated explosions, but can also emerge from ongoing, violent relationships between stars. The vampire star is simultaneously mesmerizing and terrifying, a perfect example of the universe's capacity for continuous, relentless, and intelligent feeling destruction, sculpting the cosmos in ways that are as beautiful as they are deadly. Collapsar stars, the birth of black holes. Collapsar stars are among the most terrifying and enigmatic phenomena in the universe, representing the ultimate shortcut to cosmic annihilation. Unlike typical massive stars that end their lives in explosive supernovae, collapsars bypass the spectacular outward blast and instead collapse directly into black holes. This process is silent, yet infinitely more dangerous in its implications because it represents a star vanishing into a gravitational abyss while potentially launching highly focused relativistic jets, capable of irradiating regions of space tens of thousands of light-years away. These stars are the progenitors of long-duration gamma-ray bursts, GRBS, among the most energetic and deadly events known in the cosmos. A collapsar doesn't just die, it transforms into a cosmic predator, creating an energy beam that, if pointed toward a nearby planetary system, could sterilize life entirely. The formation of a collapsar begins with a massive star, typically at least 25 to 30 times the mass of the Sun. These stars burn fuel at furious rates, building up layers of increasingly heavy elements until the core is dominated by iron. Iron fusion is endothermic, meaning it absorbs energy rather than releasing it, and when the core reaches a critical mass, it becomes unable to support itself against gravity. Unlike stars that explode in supernovae in a collapsar, the core's mass is so great that the gravitational collapse is immediate and complete. The stellar envelope plunges inward at relativistic speeds, crushing the core into a singularity, a black hole, almost without warning. There is no outward blast to disperse the star's outer layers. Instead, much of the mass may fall directly into the black hole, while the remaining material forms a hyperaccreting disk that powers twin jets along the star's rotational axis. These jets, moving near light speed, can produce gamma-ray bursts that are concentrated beams of lethal radiation. Gamma-ray bursts from collapsar stars are extraordinary in scale. These events can release as much energy in a few seconds as the Sun would emit over its entire 10 billion year lifetime. For a planet in the direct path of a GRB, the consequences are apocalyptic. The gamma rays could strip away the atmosphere, destroy the ozone layer, and irradiate the surface with lethal doses of high-energy photons. Even planets at a safe distance can experience profound disruptions to their atmospheric chemistry, while nearby interstellar material can be ionized and heated, altering star formation and galactic dynamics on massive scales. The universe, through these stars, demonstrates that destruction does not require proximity. The energy is sufficient to wreak havoc across entire star systems and potentially affect life across vast stretches of space. Collapsar stars are rare, but their rarity only amplifies their terror. Because these stars bypass the supernova stage, they are often difficult to detect until the black hole and jets are formed. Astronomers rely on gamma-ray observatories and afterglow measurements to infer their presence, reconstructing events that occurred millions or even billions of light years away. The combination of invisibility until the point of destruction and the unimaginable energy released during the event makes collapsars a perfect cosmic stealth threat. A star can quietly live out its massive life, only to vanish in a catastrophic collapse that emits concentrated, lethal radiation across the universe. The mechanics of collapsar jet formation are also deeply fascinating and terrifying. As material falls into the newly formed black hole, the accretion disk becomes incredibly hot, and magnetic fields are twisted into tight configurations. This process converts gravitational energy into kinetic and radiative energy, producing jets that pierce through the collapsing star and extend into interstellar space. These jets are not uniform. They are turbulent, variable, and capable of creating massive shocks as they collide with surrounding gas. In effect, a collapsar does not simply vanish. It broadcasts its death in violent, concentrated beams of energy. For any observer fortunate enough to see such an event in a distant galaxy, it would appear as a sudden, brilliant flash of light. But for those hypothetically close enough, it is an extinction-level event. Collapsars also challenge astrophysicists' understanding of stellar evolution. The direct collapse into a black hole without a supernova implies that our models of mass loss, angular momentum, and core dynamics must accommodate extreme conditions. These stars reveal that stellar death is not always explosive in the classical sense, and that the universe can produce deadly outcomes that are both sudden and silent. Their study has refined models of black hole formation, jet physics, and gamma-ray burst mechanics, offering insight into some of the most extreme processes known. Yet every new collapsar observed reinforces a terrifying truth. The cosmos contains mechanisms for total annihilation that do not require large, visible explosions. Sometimes, disappearance is far deadlier than eruption. Philosophically, Collapsar stars underscore the hidden dangers of the universe. Unlike supernovae or magnetars, whose danger can often be inferred from their brightness or activity, collapsars hide their lethal potential until the moment of transformation. They are cosmic predators lying in wait, and their destruction can extend across galactic scales. For life in any planetary system unlucky enough to be aligned with the jets, there is no warning, no defense, and no chance of survival. They are a stark reminder that the universe is indifferent, capable of instantaneous, silent, and concentrated destruction, a warning that even the most stable-appearing stars can harbor the seeds of apocalypse. Thorne-Zytkow objects, the Frankenstein stars. These stars are among the most bizarre and terrifying constructs the universe has ever produced, earning the nickname Frankenstein stars because of their unnatural and hybrid nature. Unlike conventional stars, these objects are not simple, isolated balls of gas fusing elements in their cores. Instead, they are the result of a bizarre cosmic merger between two extreme objects, a neutron star and a normal, massive companion star. In a Thorne-Zytkow object, TZO, the dense neutron star core resides inside a much larger supergiant envelope, creating a star that fuses elements in exotic ways and behaves in ways that defy conventional stellar physics. These stars are not just curiosities, they are potential laboratories for the most extreme conditions in the universe, where gravity, density, and energy combine to create phenomena that are simultaneously fascinating, mysterious, and deadly. The formation of these stars is a violent process. A neutron star, itself the compact remnant of a previous supernova, must collide with or be captured by a massive companion star. Typically, this occurs in a binary system where orbital decay or a catastrophic event drives the two stars together. As the neutron star plunges into the larger star's envelope, it sinks toward the core due to gravitational drag. Once embedded, the neutron star begins accreting matter from the surrounding envelope, generating immense heat, pressure, and localized nuclear reactions that would be impossible in a normal star. This unique configuration produces a star with unusual properties. The core's extreme density modifies the surrounding stellar structure, while the envelope continues to undergo conventional fusion, producing a hybrid system that is both unstable and extraordinarily energetic. The very existence of these stars challenges traditional astrophysics, demonstrating that the universe can assemble structures that seem unnatural yet perfectly feasible under extreme conditions. One of the most terrifying aspects of these stars is their unpredictability. The neutron star at the core can siphon mass from the envelope at uneven rates, potentially triggering localized explosions, sudden expansions, or bursts of high-energy radiation. The envelope itself, distorted by the gravitational pull of the neutron star, can develop unusual convection patterns and unstable fusion zones. These stars may also produce unusual nucleosynthesis, forming elements that cannot typically be produced in ordinary stellar cores, such as certain heavy isotopes of lithium or rubidium. In effect, these stars are cosmic alchemists, creating strange and exotic matter in the most violent and unusual conditions imaginable. For hypothetical planets in the vicinity, a Thorne-Zytkow object could produce unpredictable bursts of radiation or stellar wind, creating an environment that is not only lethal but impossible to anticipate. The observational characteristics of these stars add to their eeriness. From Earth, these stars appear as supergiants with unusual spectral signatures, often slightly cooler than expected for their size, but exhibiting peculiar abundances of heavy elements. Detecting a TZO is extremely difficult because the neutron star is hidden inside the massive envelope, making direct observation nearly impossible. Instead, astronomers infer the presence of a TZO through indirect signatures, such as anomalous chemical abundances or unexplained luminosity variations. This hidden, enigmatic nature of the star mirrors its internal violence. While it may look relatively ordinary from the outside, the interior hosts a neutron-star core devouring material and altering the star's behavior in ways that could never occur naturally in a conventional star. The contrast between exterior calm and interior chaos makes these stars some of the most unsettling objects in the galaxy. In terms of cosmic danger, these stars represent a slow-burning but persistent threat. They are not prone to instant explosions like supernovae, nor do they unleash immediate gamma-ray bursts like collapsars. Instead, the danger comes from the extraordinary energy concentrated inside a seemingly benign star, waiting for conditions that could trigger sudden outbursts, mass ejections, or violent stellar flares. The neutron-star core can destabilize the envelope over time, potentially leading to partial eruptions or catastrophic collapse. Furthermore, if the TZO eventually exhausts its fuel, or the neutron star accretes enough material, the star could collapse into a black hole, unleashing a sudden and potentially violent end. This combination of unpredictability, hidden power, and extreme energy output makes Thorne-Zytkow Objects a unique and terrifying class of star, an ongoing cosmic experiment in destruction and instability. From a scientific perspective, these stars are invaluable. They offer rare opportunities to study extreme nuclear reactions, the behavior of matter under ultra-high densities, and the interactions between a neutron star and stellar envelope. Observing and modeling these stars challenges astrophysicists to extend existing theories of stellar evolution, binary interactions, and nucleosynthesis. Yet while they provide critical insights into astrophysical extremes, the very same processes that make them scientifically intriguing also render them frightening. They embody a universe that is willing to experiment with extreme configurations, creating living, hybrid engines of energy and destruction that defy ordinary understanding. PSR J2032+4127, the Doomsday Binary. This star is one of the most formidable and dangerous binary systems known, earning the ominous nickname the Doomsday Binary due to the extreme interactions occurring between its two stellar components. It is a pulsar locked in a tight, highly eccentric orbit around a massive companion star, creating an environment of continual cosmic violence. Unlike isolated pulsars that emit radiation into the void, this star's proximity to its massive partner means that the pulsar's energetic winds and magnetic fields constantly collide with the companion's stellar material. These interactions produce high-energy radiation, shockwaves, and turbulent stellar winds, turning the binary into a cosmic maelstrom. For nearby objects or planets in the system, this is a perpetual zone of deadly energy, illustrating how binary interactions can be as hazardous as gamma-ray bursts or magnetars. The pulsar in this system rotates at extraordinary speed, emitting beams of electromagnetic radiation from its magnetic poles. As it sweeps past the companion star, these beams interact with the dense stellar winds of the massive partner, producing violent X-ray and gamma-ray emissions. The periodic closeness of the orbit causes the intensity of these interactions to fluctuate dramatically, leading to bursts of radiation strong enough to alter surrounding interstellar material. In essence, this star acts like a cosmic particle accelerator, accelerating charged particles to near-light speeds and producing a persistent flood of high-energy radiation. The violent interplay between the pulsar's wind and the massive star's outflow creates a system where energy is constantly redistributed in chaotic, unpredictable ways, making it one of the most extreme laboratories for high-energy astrophysics. One of the most terrifying aspects of this star is the potential for catastrophic events during periastron, when the pulsar comes closest to its companion. At these points, The gravitational forces and magnetic interactions are at their maximum, causing sudden increases in radiation output, shock formation, and possible mass ejections from the massive star. These outbursts are not just visually spectacular, they are destructive forces that can reshape the immediate stellar environment. Hypothetically, any planets orbiting nearby would face lethal doses of X-rays and gamma rays, while interstellar clouds in the vicinity could be ionized and heated, disrupting star formation. The doomsday binary demonstrates that the danger of stars is not only in isolated explosions, but can also arise from sustained, high-energy interactions between closely bound stellar companions. The orbital mechanics of this star make it uniquely fascinating and terrifying. The pulsar's orbit is highly elongated, meaning that the distance between it and the massive star varies greatly over its orbital period. This eccentricity creates cycles of calm and extreme activity, where energy output can spike dramatically over short timescales. These variations provide astronomers with invaluable observational data, revealing how pulsar winds interact with dense stellar envelopes and how binary systems evolve under extreme gravitational and magnetic forces. At the same time, they underline the inherent danger of the system. The pulsar is not merely a background hazard, but a continuously interacting agent capable of producing unpredictable and lethal energy releases whenever the orbital geometry aligns unfavorably. From a physics perspective, this star is a treasure trove of extreme conditions. The interplay between the pulsar's magnetic field and the companion star's stellar wind creates relativistic shocks, accelerates particles, and produces radiation across the electromagnetic spectrum. These processes allow scientists to study fundamental principles of magnetohydrodynamics, particle acceleration, and high-energy radiation, all within a naturally occurring laboratory in space. Yet while this provides immense scientific value, it also highlights the system's potential for cosmic violence. Unlike supernovae, which occur as singular catastrophic events, the doomsday binary produces a continuous, dynamic, and dangerous energy environment that could destroy anything unlucky enough to exist within close proximity. The star's danger is amplified by the unpredictability inherent in its interactions. The massive star may experience irregular mass ejections, stellar flares, or sudden increases in wind density, all of which interact violently with the pulsar's magnetic field and energetic outflows. These interactions can produce asymmetric radiation bursts and localized explosions of energy that ripple through space. The system is not static. It is a constantly evolving high-energy environment where physics operates at extremes. For hypothetical observers nearby, this would be an unrelenting cosmic storm, with lethal radiation and charged particle bombardment occurring in cycles that are impossible to predict. Philosophically, this star serves as a reminder that cosmic threats are not always sudden or explosive. They can also be sustained and persistent. The doomsday binary embodies a slow-burn kind of apocalypse, where danger is ever present, dictated by orbital mechanics, stellar winds, and pulsar emissions. It teaches us that in the universe, destructive power is not limited to one-off events like supernovae or gamma-ray bursts. Ongoing stellar interactions can be equally deadly, producing environments where energy and gravity conspire to create conditions that are fundamentally inhospitable to life. In conclusion, this star is one of the most extreme and terrifying binary systems in existence. Its pulsar companion configuration produces sustained, high-energy radiation, violent shockwaves, and unpredictable bursts of activity, creating a cosmic arena of destruction. The doomsday binary is not only scientifically fascinating, but also a stark illustration of the universe's capacity for continuous, intricate, and deadly forces. It exemplifies how stars can interact to amplify danger, proving that even the most ordinary-looking stellar neighbors can hide extraordinary and lethal energy dynamics. This star is a vivid reminder that in the cosmos, destruction can be constant, intricate, and entirely unavoidable. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.